Madam, welcome.
Namaskara.
Start madam, sir.
Hi, sir.
Good evening, all the participants. Madam, there are participants who will join on YouTube. They find YouTube easier to join.
Okay.
That's why they are more on YouTube platform than in Cisco WebEx.
Okay.
We'll start, madam. Good evening, everybody. We have with us Srimati M.K. Uma, madam. She will be speaking on adventures of Simple Pendulum. Let me briefly tell about the academic background of Madam and achievements. Madam has completed her BSc and MSc from Kerala University. Later completed her B.Ed from Utkal University. Madam has worked as a teacher in Bhavan's Vidya Mandir, Cochin. Then later worked as a lecturer in our own NMKRV College. After that, she was principal in DAV School, Bhubaneswar. Also, she was a teacher in physics and mathematics in Mumbai, then PGT and HOD in Manav Sthali School in New Delhi. And also she was a resource expert in Anveshaka in New Delhi, Bangalore and Mysore. She has more than 30 years of experience as a teacher and lecturer in physics and mathematics in Cochin, Bangalore, Bhubaneswar, Mumbai and Delhi. She has established a CBSE school under DAV banner and possesses the experience in administration and school management as principal of DAV Public School in Bhubaneswar. She has ably started and organized astronomy club, robotics club, science club in New Delhi. She has also been a resource expert associated with Anveshaka in New Delhi, Bangalore and Mysore. With this background, I request Madam to deliver a talk on great adventures of Simple Pendulum. Madam, over to you for your
Thank you so much. Thank you very much. Elrigu namaskara. Good evening. I understand that this is mainly attended by the PUC students.
Yes, madam.
So, ಅಲ್ವಾ
ಹೌದು.
ಅದಕ್ಕೆ ನಾನು PUC ಸ್ಟೂಡೆಂಟ್ಸ್ ಹತ್ರ ಮಾತಾಡ್ತಿದ್ದೀನಿ ಅನ್ಕೊಂಡು ನೀವು ಎಲ್ಲರೂ ನಮ್ಮ ಸ್ಟೂಡೆಂಟ್ಸ್ ಅಂತ ಅನ್ಕೊಂಡು ಮಾತಾಡ್ತೀನಿ.
ಆಯ್ತು ಮೇಡಮ್.
So today I'm really happy that I have got this opportunity and I thank the Karnataka Science and Technology Academy for giving me this opportunity to share my views or share my story of the Simple Pendulum with you all. Simple Pendulum ಅನ್ನೋದು ನಮ್ಗೆಲ್ರಿಗೂ ಗೊತ್ತು. ನಾವು ಚಿಕ್ಕಂದಿನಿಂದ ಗಡಿಯಾರ ನೋಡ್ತಾ ಇದ್ದೀವಿ, ಗ್ರ್ಯಾಂಡ್ ಫಾದರ್ ಕ್ಲಾಕ್ ಅಂತಾನು ನೋಡ್ತಿರ್ತೀವಿ. ವಾಟ್ ಇಸ್ ದಿಸ್ ಗ್ರ್ಯಾಂಡ್ ಫಾದರ್ ಕ್ಲಾಕ್? ಅಲ್ಲಿ ಒಂದು ದೊಡ್ಡ ಪೆಂಡುಲಮ್ ಇರೋದು, ಅದು ಮೂವ್ ಆಗ್ತಾ ಇರೋದು ಟು ಅಂಡ್ ಫ್ರೋ. It was a toy for all of us when we were very young, but we have never thought that time that it has got a lot of ideas behind it, that is ideas about motion and force. ಇದಕ್ಕೆ ಮುಂಚೆ ನಾವು, before we go to the pendulum, just basic things about the pendulum I would like to share with you. The pendulum is a heavy bob suspended by a thin string and suspended from a point of suspension from a rigid support. In the mean position, this is the mean position. ಇಲ್ಲಿಂದ ನಾವು ಇದನ್ನ ಮೂವ್ ಮಾಡಿದ್ರೆ ಈ ಪಾಯಿಂಟ್ಗೆ, this extreme position or this is the maximum displacement position, ಅದನ್ನ ಆಂಪ್ಲಿಟ್ಯೂಡ್ ಅಂತ ಕರಿತೀವಿ. The length of the pendulum is from the point of suspension to the center of the bob. So it is a heavy weight. Basically, it's a heavy weight suspended from a fixed point so that it can swing freely. ಇದು freely move ಮಾಡುವಾಗ ಅದ್ರ ಮೋಷನ್ ನ ನೋಡಕ್ಕೆ ಬಹಳ ಚಂದ ಇರುತ್ತೆ. Now let us start the story. We are starting the story in Italy. Flashback time machine ಅಲ್ಲಿ ಹೊಟ್ಟೋಗೋಣ ನಾವು. We'll go to Italy 1583, 16th century. 1583 ಹೋಗೋಣ. Let us go to a cathedral in Italy, in Pisa. ಆ ಕ್ಯಾಥೆಡ್ರಲ್ ಒಳಗಡೆ ಒಂದು ಶ್ಯಾಂಡೇಲಿಯರ್ ಅಂತ ಲ್ಯಾಂಪ್ ಇತ್ತು. ಅವಾಗಿನ ಕಾಲದಲ್ಲಿ ಕ್ಯಾಂಡಲ್ ಹಚ್ಚೋರು, ಆಮೇಲೆ ಅದನ್ನ ಸ್ವಿಂಗ್ ಆಗೋದದು. So there was a lamp lighter who lighted the lamp. For lighting the lamp, he had to pull the lamp or the chandelier towards himself. He lighted the lamp and let it go. It started moving to and fro. There was a young, energetic boy in his late teens over there who was watching this action taking place. ಈ ಸ್ವಿಂಗ್ ಆಗ್ತಾ ಇರೋದು ಎಡ ಬಲ ಟು ಅಂಡ್ ಫ್ರೋ ಆಗ್ತಾ ಇರೋದು ನೋಡಿ, he watched for some time, then he felt his pulse and then he compared the swing of the pendulum to the pulse on his wrist. Any guesses on who he was? Anyway, let me go ahead with this. It was, of course, the father of modern physics, Galileo Galilei. So today we will study about the properties of pendulum as discovered by Galileo Galilei. Illinda ನಾವು will go up to another 130 years or maybe 200 years almost, till 1930s ಹೋಗೋಣ. ಅಲ್ಲಿ ತನಕ ಈ ಪೆಂಡುಲಮ್ ಎಷ್ಟು ಇಂಪಾರ್ಟೆಂಟ್ ರೋಲ್ ಪ್ಲೇ ಮಾಡಿದೆ ಅಂತ let us just see. So Galileo Galilei was born in 1564. He was the oldest son. He was the oldest son of Vincenzo Galilei. Vincenzo Galilei himself was a great musician. He was brought up under his able parenthood. Vincenzo Galilei always told that experiments have to be conducted to believe anything. So Galileo was brought up to believe that any claims made theoretically had to be checked experimentally. So in 64 in the 1581, almost when he was 17 years old, he joined as a medical student in the University of Pisa. Later on, he found that he was not much interested in the medicine. Onge mathematics al tumba interest ittu. So he became a college dropout, convinced his father, and he came back to Florence. Can you imagine? He became a professor of mathematics at the same University of Pisa in 1589. And it was here that he conducted a lot of experiments, and the very famous experiment of dropping a heavy and light object from a great height, great tower, and proving that the speed of the fall of an object does not depend on its weight. Earlier the whole world believed Aristotle's thoughts, and he said that the speed of the object depends on its weight. Now he disproved it. So this was the beginning of a modern era in science. That is, the assertions about any physical quantity or in the physical world, however wise or respected people, ಯಾರು ಎಷ್ಟೇ ಇಂಪಾರ್ಟೆಂಟ್ ಪೀಪಲ್ ಏನೇ ಹೇಳಿ assertions ಮಾಡಲಿ, assumptions ಮಾಡಲಿ, you should not believe them. You should experimentally test them. Only then, if they are proved, only then you should believe in them, or they stand or fall by the experimental test. So ಇದು ಈ heavy and light body same time fall ಮಾಡುತ್ತೆ ಅನ್ನೋದಕ್ಕೆ in later somewhere he has quoted that he had observed the hailstones falling during the hailstorm. He observed that the heavy hailstorm, big, large and small hailstones fell at the same time. That was the reason he came to this conclusion. Somewhere I read about it. Now let us go to 1602. From 1590 to 1602. He remembered the pendulum which he had seen in the cathedral. He wanted to study the motion of pendulum. He really wanted to check if the period was always same for everything. Whether length changed, whether the mass changed, or whether the amplitude, we say distance, the maximum extreme displacement was changed. He wanted to study about that. In the meantime, the constancy of the period made him devise an instrument, pulsilogia, to read the pulse of patients. Now let us see the experiments what he had conducted by this video. Of course, this video is a recent one, and we can have an idea of what experiments he did. Galileo first took two pendulums, identical, that is having the same mass, same length, but he displaced them through different angles, or the displacement was different. He released them simultaneously. He observed that they passed the mean position at the same time, no matter from there they were suspended. They were released. See, lodile. Simultaneously, they have been released from different positions. They come to the mean position at the same time. This is called as the law of amplitudes or law of isochrony. Next, a heavy mass, heavy bob, and a light bob were used. Released from the same position. Again, the same conclusion, the time period was the same whether it was a heavy bob or a light bob. So the time period of the simple pendulum is independent of the mass. Next, two bobs were taken of the same mass but different lengths, but they were released from the same displacement. Here is what he saw, that the periods were not same for the two. He conducted this experiment taking 1/4 of the length of the bob, 1/6, 1/8, and so on, 4 times, 8 times, and so on. Finally, he came to the conclusion, after repeating a number of times, he came to the conclusion that the changing length of the pendulum made a change in the time period, or T, the time period T is directly proportional to the square root of the length of the pendulum. From this, he could make a connection between the planets which orbit the sun. He said the planets which are farther from the sun, they orbit slowly than the ones which are nearer. That means the one which are nearer, their speed, their time period is shorter because they are moving faster compared to the. Then he wanted to study, in this was the case he found out. So from this he wanted to study the motion of objects, because he had already seen the free fall motion. He had proved that the objects fall at the same time. For this he had to find out the time taken by the body to fall freely from a height. The bodies fell so quickly, he was not able to take the accurate measurements of time. So he wanted to slow down the gravity or dilute the gravity to observe the rate of increase of speed, or he wanted to study the rate of acceleration in slow motion. So what could he do? He devised a very great instrument, inclined plane. He argued that the rate of descent in inclined plane is slower than that of a freely falling body. The freely falling body moves only vertically downward. If vertical board na ನಾವು gradually ಹಿಂಗೆ bend ಮಾಡಿದ್ರೆ we get an inclined plane. ಅದನ್ನ ಇನ್ನು ಮಾಡ್ತಾ ಹೋದ್ರೆ we get a inclined plane which is having a very small angle of inclination. ಕಾಣಿಸ್ತಾ ಇದೆಯಾ ಈ ಲಾಸ್ಟ್ ಡಯಾಗ್ರಾಮ್? Okay. So he argued that this motion and this motion will be similar. Only thing is the motion will be slow in this, and it was easier for him to time the motion. This has got only vertical motion. The freely falling body has got only vertical motion, but the body moving on the inclined plane has got both vertical and horizontal motions, but the underlying physics is same. So in the study of this inclined plane, 3 variables were involved: time, distance, and speed. So in those days, no proper instruments were there to calculate or to determine the speed of a body moving. So only things which he could measure was time and distance. So again, time had a time was used in seconds or whatever it is, but he used different units. He used to measure the length, he used punto, he used tempo to measure the time, and to measure the weight of water, he used grains. Why did he use water? To find out the time, he had taken the water clock to measure, special type of water clock which he had made. So now he was having time and distance. He took the two things which he could easily measure, and then he used the proportionality theorem of Euclid. X1, where x1, x2, y1, y2 are variables, x1 is to x2 as y1 is to y2, or x1 divided by x2 is equal to y1 divided by y2. This method eliminated the need of absolute units, taking the ratio ತಗೊಂಡಿದ್ರಿಂದ ಅವನಿಗೆ ಇದೊಂದು ಅಡ್ವಾಂಟೇಜ್ ಆಯಿತು. So next he took a very long inclined plane, let us say 1 meter ಇತ್ತು ಅಂತ ಅನ್ಕೊಳ್ಳೋಣ. He divided it into half, 1/4 and 3/4 ಮಾರ್ಕ್ ಮಾಡ್ಬಿಟ್ಟ, ಲೆಂತ್ಗಳನ್ನ ಮಾರ್ಕ್ ಮಾಡ್ಬಿಟ್ಟು, ದೆನ್ ಒಂದೊಂದು ಲೆಂತ್ಗೂ ಇಲ್ಲಿಂದ ಕ್ವಾರ್ಟರ್, ಸಪೋಸ್ ಇಲ್ಲಿಂದ ಬಂದ ಕ್ವಾರ್ಟರ್ ಆಫ್ ದ ಲೆಂತ್ ಹೋಗಕ್ಕೆ ಎಷ್ಟು ಟೈಮ್ ತಗೊಂತು, ಅರ್ಧ ಲೆಂತ್ ಹೋಗಕ್ಕೆ ಎಷ್ಟು ಟೈಮ್ ತಗೊಂತು, 3/4 ಹೋಗಕ್ಕೆ ಎಷ್ಟು ಟೈಮ್ ತಗೊಂತು, ಹಾಗೆ ಕಂಟಿನ್ಯೂಸ್ಲಿ he started measuring. So he rolled the ball down each length, timed the timing with a water clock. Then in the water clock ಅಲ್ಲಿ ಏನ್ ಮಾಡೋದು, ಇದು ಸ್ಟಾರ್ಟ್ ಮಾಡಿದಾಗ ಅದು ನೀರು ಹೋಗುತ್ತೆ, ನೀರು ಫ್ಲೋ ಆಗುತ್ತೆ. ಅದು ನಿಲ್ಲಿಸಿದಾಗ ತಕ್ಷಣ ನಿಲ್ಲಿಸಿದ್ರೆ we can wait, collect the water. He weighed the water using a very accurate balance. ಸೊ ಆ ಒಂದ್ ಲೆಂತ್ಗೂ ಇನ್ನೊಂದು ಲೆಂತ್ಗೂ ಟೈಮ್ ಕಂಡು ಹಿಡಿದ್ರೆ, ಈ ಟೈಮ್ಗೆ ಹೆಂಗ್ ಕಂಡು ಹಿಡಿಯೋದು? ವೇಟ್ ಇನ್ ಒನ್ ಕೇಸ್, divided by weight in second case gives the time in the first case divided by the time in the second case. So the difference in the ratio of these weights give the differences in the ratio of time. The special water clock which he used is called as clepsydra. ಇಲ್ಲಿಂದ ನೀರು ಹೋಗುತ್ತೆ, ಇದು collect ಮಾಡಿ. It was a very tedious process. You wouldn't believe the smallest time he could measure was 1/100th of a second, and this is the Olympic standard now. Now let us see. Ilinda he draw, when it fell down, he saw that the distances covered in each equal interval of time, or as the time passed, these distances covered, they increase by odd numbers. That is 1, 3, 5, 7. So first second alli illittu, second alli illittu, third alli illittu. Idu nodidre we see that these are the squares of the square of 1, square of 2, square of 3, etc. If we see this progression is 1, 3, 5, 7. ಇದು ಯಾವುದೇ ಇನ್ಕ್ಲಿನೇಷನ್ಗೆ ಅವನು ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಮಾಡಿದ ಡಿಫ್ರೆಂಟ್ ಆಂಗಲ್ ಆಫ್ ಇನ್ಕ್ಲಿನೇಷನ್ಸ್ ಥೀಟಾ ತಗೊಂಡ್ರು he got the same value. ಇದೇ ಸಿಕ್ತು. ಸೇಮ್ ವ್ಯಾಲ್ಯೂ ಅಂದ್ರೆ ಇದೇ ತರ 1:3:5 1, 3, 5, 7 ಇಂದ ಹೋಯ್ತು. So he could conclude that there is simplest kind of relationship between velocity and time, and definitely the distance traveled is proportional to the square of the time taken for it. So now he found out that the free falling objects accelerate uniformly. The distance covered is proportional to the square of time. ಇವತ್ತಿನ ದಿನ ನಮಗೆ ಗೊತ್ತು ಈ second equation of motion, S is equal to ut plus half at square. For a freely falling
Hello.
ಡಿಸ್ಕನೆಕ್ಟ್ ಆಯ್ತು, ಕಾಲ್ ಮಾಡಿ ಮೇಡಮ್ಗೆ.
ಕಾಲ್ ಮಾಡ್ತೀನಿ. ಡಿಸ್ಕನೆಕ್ಟ್ ಆಯ್ತು. ನೀವು ಸ್ಲೈಡ್ ಚೇಂಜ್ ಮಾಡುವಾಗ ಎಕ್ಸ್ ಬಟನ್ ಒತ್ತಿದ್ರ ಅಂತ ಕಾಣುತ್ತೆ. ಸೊ ಡಿಸ್ಕನೆಕ್ಟ್ ಆಯ್ತು, ಮತ್ತೆ ರೀಜಾಯಿನ್ ಮಾಡಿ ಮೇಡಮ್. ಹೌದೌದು, ಮೋಸ್ಟ್ಲಿ ನೀವು ಸ್ಲೈಡ್ ಚೇಂಜ್ ಮಾಡ್ಬೇಕಾದ್ರೆ ಅದು ಎಕ್ಸ್ ಮಾರ್ಕ್ ಅಲ್ಲಿ ಪ್ರೆಸ್ ಆಯ್ತು ಅಂತ ಕಾಣುತ್ತೆ, ಅದಕ್ಕೆ ಡಿಸ್ಕನೆಕ್ಟ್ ಆಯ್ತು. ಮತ್ತೆ ರೀಜಾಯಿನ್ ಮಾಡಿ ಮೇಡಮ್. ಅದೇ ಮೆಸೆಂಜರ್ ಲಿಂಕ್ ಇದೆಯಲ್ಲ, ಅದಕ್ಕೆ ಹೋದ್ರೆ ಆಯ್ತು. ಯಾ, I request the participants to be online. Madam will be back soon. It's a small mistake happened from our side. I apologize. Hello. ಹೌದಾ? ಇಲ್ಲ, ಏನ್ ಹೇಳ್ತಾ ಇದ್ದಾರೆ ಹೇಳಿ ಸ್ಕ್ರೀನ್ ಅಲ್ಲಿ. ಸ್ಟಾರ್ಟಿಂಗ್ ವೆಬ್ಎಕ್ಸ್ ಅಂತ ಇದೆಯಾ? ಹಾಗಾದ್ರೆ ಇಂಟರ್ನೆಟ್ ಸ್ವಲ್ಪ ಡೌನ್ ಆಗಿರ್ಬೇಕು ಅಂತ ಕಾಣುತ್ತೆ, ಅದಕ್ಕೆ. ಹೌದಾ ಮೇಡಮ್, ಒಂದು ಕೆಲಸ ಮಾಡಿ, ಅದು ಆಫ್ ಮಾಡಿ ಮತ್ತೆ ರೀಜಾಯಿನ್ ಅಂತ ಕೊಡಿ. ಇಲ್ಲಾಂದ್ರೆ ಇವಾಗ ಮತ್ತೆ ಇದು ಕಳಿಸ್ತೀನಿ, ನಿಮ್ಗೆ ರಿಮೈಂಡರ್ ಕಳಿಸ್ತೀನಿ ಇನ್ನೊಂದ್ಸಲ. ಹಾ ಕಳಿಸ್ತೀನಿ ಒಂದೇ ನಿಮಿಷ ಮೇಡಮ್. ಮೇಡಮ್ ಒಂದು ನಿಮಿಷ UMA.MK9@gmail.com ಅಲ್ವಾ? ಓಕೆ, ಎಸ್ ಮೇಡಮ್, ಮೇಲೆ ಕಳಿಸಿ ನೋಡಿ ಮೇಡಮ್, ಇನ್ಬಾಕ್ಸ್ ರಿಫ್ರೆಶ್ ಮಾಡಿ ಮೇಡಮ್. ಮೇಡಮ್ PPT ಶೇರ್ ಮಾಡಿ ಮೇಡಮ್. ನೀವು ಸ್ಲೈಡ್ ಅಲ್ಲಿ ಇದ್ರಲ್ಲ, ಅದೇ ಸ್ಲೈಡ್ ಇಂದ ಸ್ಲೈಡ್ ಶೋಗೆ ಹೋಗಿ ಸ್ಲೈಡ್ ಶೋ ಫ್ರಮ್ ದಿಸ್ ಕರೆಂಟ್ ಅಂತ ಕೊಡಿ. ಒಂದು ನಿಮಿಷ, ಮೈಕ್. ಯಾ ಫೈನ್, ಯು ಕ್ಯಾನ್ ಗೋ ಆನ್ ಮೇಡಮ್.
Now conclusions ಮಾಡಿದ್ದೇನು ಅಂದ್ರೆ ಫ್ರೀ ಫಾಲ್ we were till here distance is proportional to time square. ಬಟ್ ಇವತ್ತಿನ ದಿನ ನಮ್ಗೆ ಗೊತ್ತು ಈಕ್ವೇಶನ್ ಆಫ್ ಮೋಷನ್ S is equal to UT plus half AT square ಅಂತ. U ಅಂದ್ರೆ ಇನಿಷಿಯಲ್ ವೆಲಾಸಿಟಿ. ಇಫ್ ಇಟ್ ಇಸ್ ಹ್ಯಾವಿಂಗ್ ಎ ಫ್ರೀ ಫಾಲ್, ಇನಿಷಿಯಲ್ ವೆಲಾಸಿಟಿ is 0. And then A ಅಂದ್ರೆ acceleration. So that is acceleration due to gravity, in this case small g. So in this case distance D is proportional to half GT square ಅಂತ ಬರುತ್ತೆ. U 0 ಅದರಿಂದ T 0 ಆಗುತ್ತೆ. U into T 0 ಆಗುತ್ತೆ. So we come to the conclusion that D is proportional to T square. This he had got long back. He was the first person to get this, Galileo. So now he could relate the motion on the free fall to the motion on the inclined plane. So this was the first equation which he got. D is proportional to T square. But now there was a problem in this. The factor which he could not eliminate was the friction in the case of a inclined plane. It was then that he remembered the motion of the pendulum. So motion of the pendulum was related to free fall. Then we can relate the motion of the pendulum to the inclined plane. So free fall to inclined plane to pendulum he had gone. So pendulum released from the same position at the free fall's height will have the same acceleration like that of a ball dropped from the rest. So we see from here that bari observation matra alla, mathematics and experiment guided by mathematics played a major role in his discovery. Ivaga what was the experiment he conducted? One free fall ge one body tagondu, very heavy body tagondu adanna drop ಮಾಡ್ದ. ಅದು ಡ್ರಾಪ್ ಫ್ರಮ್ ಸಮ್ ಒನ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಹೈಟ್ H ಅಂತ ತಗೊಳ್ಳೋಣ. ಅದು ಕೆಳಗಡೆ ಬಿದ್ದಾಗ ಒಂದು ಬೋರ್ಡ್ ಮೇಲೆ ಬಿದ್ದಾಗ ಧಡ್ ಅಂತ ಶಬ್ದ ಬರುತ್ತೆ. ಸೊ ನಾವು ಇವಾಗ ಅದೇ ಮಾಸಿನ ಪೆಂಡುಲಮ್ ತಗೊಂಡು he lifted it to the same height as this, and then he tried to find the length of the pendulum for which it would come to the lowest position. ಅದೇ ಟೈಮ್ ಇದೇ ಶಬ್ದ ಕೇಳೋಕೆ ಮಾಡೋದಕ್ಕೋಸ್ಕರ ಒಂದು ವಾಲ್ ಇಟ್ಬಿಟ್ಟ, ಇದೇ ಬೋರ್ಡಿನ ವಾಲ್ ಇಲ್ಲಿ ಇಟ್ಬಿಟ್ಟ. ಬಿಕಾಸ್ ಹೈಯೆಸ್ಟ್ ಪೊಸಿಷನ್ ಟು ಲೋಯೆಸ್ಟ್ ಪೊಸಿಷನ್ ಬರ್ಬೇಕಂದ್ರೆ ಇದು ಹೈಯೆಸ್ಟ್ ಪೊಸಿಷನ್ ಇಂದ ಲೋಯೆಸ್ಟ್ ಪೊಸಿಷನ್ ಬರ್ತಾ ಇದೆ. ಸೊ ಡೆಫಿನೆಟ್ಲಿ ಇಟ್ ಈಸ್ 1/4 ಆಫ್ ದ ಆಸಿಲೇಷನ್. ಸೊ 1/4 ಆಫ್ ದ ಆಸಿಲೇಷನ್ ಟೈಮ್ ಪೀರಿಯಡ್ ಕಂಪ್ಲೀಟ್ ಮಾಡೋದಕ್ಕೆ ಅದು ಅದೇ ಟೈಮಲ್ಲಿ ಶಬ್ದ ಬರೋದಕ್ಕೆ ಎಷ್ಟು ಲೆಂತ್ ಆಫ್ ದ ಪೆಂಡುಲಮ್ ಬೇಕು ಅಂತ ಕಂಡುಹಿಡ್ದ. ಹಿ ಫೌಂಡ್ ಔಟ್ ದಟ್ ದಿಸ್ ಲೆಂತ್ ವಾಸ್ ದ ಸೇಮ್. ನಾವು ಇದನ್ನ ನಾವು ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಮಾಡೋಣ. ಹಿ ಫೌಂಡ್ ಔಟ್ ದ ಟೈಮ್ ಪೀರಿಯಡ್ ಫಾರ್ ದಿಸ್, ಹಿ ಫೌಂಡ್ ಔಟ್ ಟೈಮ್ ಟೇಕನ್ ಫಾರ್ ದಿಸ್, ಟೈಮ್ ಟೇಕನ್ ಫಾರ್ ದಿಸ್ ಟು ಫಾಲ್ ಫ್ರಮ್ ಹಿಯರ್ ಟು ಹಿಯರ್. ಹಿ ಟುಕ್ ದ ರೇಷಿಯೋ ಅಂಡ್ ಇದನ್ನ ಅವನು ಬೇರೆ ಬೇರೆ ಹೈಟ್ಗೆ ಕಂಪೇರ್ ಮಾಡಿ T1 T2 T1 T2 T1 T2 ಕಂಪೇರ್ ಮಾಡಿ T1/T2 he found out that it was constant for all the values, all the heights of displacement. Now ಇವಾಗ ಇದು ಕಾನ್ಸ್ಟೆಂಟ್ ಅಂತ ಕಂಡುಹಿಡಿದ. ಟೈಮ್ ಟೇಕನ್ ಫಾರ್ ಫ್ರೀ ಫಾಲ್ T1, ಟೈಮ್ ಟೇಕನ್ ಫಾರ್ 1/4 ಆಸಿಲೇಷನ್ T2 ಕಾನ್ಸ್ಟೆಂಟ್. ನಾವು ಇವತ್ತಿನ ದಿನ ನಾವು ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಮಾಡೋಣ. ನಮ್ಗೆ ಹೇಗಿದ್ರು ಈಕ್ವೇಶನ್ಸ್ ಎಲ್ಲ ಗೊತ್ತಲ್ಲ. ಸೊ ನಾವು T1 ಡ್ಯಾಶ್ ತಗೊಂಡು T2 ಡ್ಯಾಶ್ ತಗೊಂಡು ಲೆಟ್ ಅಸ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಯೂಸಿಂಗ್ ದಿ ಈಕ್ವೇಶನ್ H is equal to half GT². ಈಗ ತಾನೇ ಹೇಳಿದ್ದೆ ನಾನು. ಇದರಿಂದ ನಮ್ಗೆ ವ್ಯಾಲ್ಯೂ ಆಫ್ G ಏನಂತೆ ಬರುತ್ತೆ, T is equal to square root of 2H/G ಅಂತ ಬರುತ್ತೆ. ಸೊ ಇದರಿಂದ ನಾವು ತಗೊಂಡ್ಮೇಲೆ ನೆಕ್ಸ್ಟ್ ಯೂಸಿಂಗ್ ದಿ ಈಕ್ವೇಶನ್ ಫಾರ್ ದ ಸಿಂಪಲ್ ಪೆಂಡುಲಮ್. ದಿಸ್ ಈಕ್ವೇಶನ್ ಅವಾಗ ಗ್ಯಾಲಿಲಿಯೋ ಗೊತ್ತಿರಲಿಲ್ಲ, ಇದು ಕ್ರಿಶ್ಚಿಯನ್ ಹೈಗಿನ್ಸ್, ಹಿ ವಾಸ್ ದ ಒನ್ ಹೂ ಗಾಟ್ ದಿಸ್ ಫಾರ್ಮುಲಾ ಫಾರ್ ದ ಸಿಂಪಲ್ ಪೆಂಡುಲಮ್. ಸೊ ಇದರಿಂದ ನಮ್ಗೆ ಏನ್ ಸಿಗುತ್ತೆ, ದಿಸ್ ಇಸ್ ಅ ಟೈಮ್ ಪೀರಿಯಡ್ ಫಾರ್ ದ ಟೋಟಲ್ ಆಸಿಲೇಷನ್. ಮೇಲಿಂದ ಕೆಳಗಿಂದ ಎಡಗಡೆ ನೆಕ್ಸ್ಟ್ ಕಡೆ ಹೋಗಿ ವಾಪಸ್ ಒನ್ ಫುಲ್ ಪೀರಿಯಡ್. ಬಟ್ ಇಲ್ಲಿ ಏನಿದೆ 1/4 ದ ಪೀರಿಯಡ್. ಸೊ ನಮಗ್ ಬೇಕಾಗಿರೋ ಪೀರಿಯಡ್ T2 ಡ್ಯಾಶ್ ಇಸ್ ಈಕ್ವಲ್ ಟು 1/4 ಆಫ್ ದಟ್ ವ್ಯಾಲ್ಯೂ. ಸೊ ಇವಾಗ ನಾವು T1/T2 ಡ್ಯಾಶ್ ತಗೊಂಡು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿ ನೋಡಿದ್ರೆ ಲೆಟ್ ಅಸ್ ಸೇ ನಮ್ಗೊಂದು x1 ಡ್ಯಾಶ್ ವ್ಯಾಲ್ಯೂ ಸಿಕ್ತು. ಅಂಡ್ ಇಫ್ ಯು ಕಂಪೇರ್ ಇಟ್ ವಿತ್ ದ ವ್ಯಾಲ್ಯೂ ವಿಚ್ ಹಿ ಹ್ಯಾಡ್ ಗಾಟ್, ಅಂಡ್ ಒಂದು ಬರ್ದಿರೋದೆಲ್ಲ ಇದೆ ನಮ್ಮ ಹತ್ರ ಅಂದ್ರೆ ಇಟ್ ಇಸ್ ದೇರ್ ಆನ್ ದ ನೆಟ್ ಆಲ್ಸೋ. ಯು ಕ್ಯಾನ್ ಸಿ ಹಿಸ್ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ಸ್ ಅಂಡ್ ದ ರಿಪೋರ್ಟ್ ಆನ್ ದಿಸ್. ವಾಟ್ ಎವರ್ ವ್ಯಾಲ್ಯೂ ಹಿ ಹ್ಯಾಡ್ ಗಾಟ್ ದೆನ್ comes to the same value, almost same value as the value which we can get by this mathematical calculations. Remember, he never wrote an equation. Galileo never used an algebraic expression. In spite of that, he could get this. So now he related free fall to pendulum. He related free fall to inclined plane. Now he is relating motion of the pendulum to the motion along the inclined plane. So he assumed this experiment was based on assumptions. Avanu experiment maadi conclusion ಗೆ ಬರಲಿಲ್ಲ. He made some assumptions and then he performed experiments to confirm his assumptions. ಯಾವಾಗಲೂ ಅವನು ಈ ಥರನೇ ಮಾಡಿದ್ದು. So he assumed that speed gained in rolling down a ramp or an incline of a given height did not depend on the slope. ಇದನ್ನ ಅವನು ಪ್ರೂವ್ ಮಾಡಬೇಕಿತ್ತು. So for this he proved this with an experiment using a pendulum and a nail. ಇಲ್ಲಿ ನೋಡಿ, ಇಲ್ಲಿ ಪೆಂಡುಲಮ್ ಸಸ್ಪೆಂಡ್ ಆಗಿದೆ. ಇಲ್ಲಿ ಅದ್ರ ಮಧ್ಯದಲ್ಲಿ ಕೆಳಗಡೆ ಒಂದು ನೇಲ್ ಇದೆ ಇಲ್ಲಿ. ಸೊ ಈ ನೇಲ್ ಇಲ್ಲದೆ ಇದ್ರೆ ಪೆಂಡುಲಮ್ ಇಲ್ಲಿಂದ ಬಿಟ್ರೆ ಇಟ್ ವುಡ್ ಹ್ಯಾವ್ ಗಾನ್ ಅಪ್ ಟು ದಿಸ್ ಲೆವೆಲ್, ಸೇಮ್ ಹೈಟ್, provided there was no air friction or any other disturbance. But ಇವಾಗ ಈ ನೇಲ್ ಇರೋದ್ರಿಂದ ಏನಾಗುತ್ತೆ, as it comes here, comes to the lowest position, it touches the nail. So the effective length becomes short at the lowest point. It hits the nail, so the effective length becomes small and the slope increases. But it is observed experimentally that it goes to the same height, comes back with the same speed, goes to the same height, comes back with the same speed, goes to the same height. So we can see this in this experiment. Observe ಮಾಡಿ carefully. ಇಲ್ಲೊಂದು ನೇಲ್ ಇದೆ. when it is moving, ಇದು ಜಸ್ಟ್ ಸ್ಟ್ಯಾಂಡರ್ಡ್ ರೆಫರೆನ್ಸ್ಗೋಸ್ಕರ ಯಾವ ಹೈಟ್ ಇಂದ ಶುರು ಆಯ್ತು, ಯಾವ ಹೈಟ್ ಇಂದ ಹೋಗಕ್ಕೆ ನೋಡಕ್ಕೆ. ಇಟ್ ಇಸ್ ಗೋಯಿಂಗ್ ಬ್ಯಾಕ್ ಟು ದ ಸೇಮ್ ಹೈಟ್. Thus he could prove that a pendulum with a nail, the motion of this whole system is similar or equivalent to the motion on an inclined plane which is connected to another incline which is more steeper, or maybe these two are having different slopes, different heights, different slopes. Exactly. So if the pendulum is released from here, comes to this point with a velocity, goes to this end, comes back with the same velocity and goes back to this motion continues. ಹಾಗೇನೆ ಇಲ್ಲಿಂದ ನಾವು ಒಂದು ಬಾಲ್ ನ ಫ್ರೀ ರಿಲೀಸ್ ಮಾಡಿದೆ, ಫ್ರಮ್ ದ ರೆಸ್ಟ್ ರಿಲೀಸ್ ಮಾಡಿದ್ರೆ ಏನಾಗುತ್ತೆ, ಅಲ್ಲಿಂದ ಇಟ್ ವಿಲ್ ರೋಲ್ ಡೌನ್, ಇನ್ಕ್ರೀಸ್ ಇಟ್ ಸ್ಪೀಡ್, ಗೋ ಅಪ್ ಟು ದ ನೆಕ್ಸ್ಟ್ ಇನ್ಕ್ಲೈನ್. ಬಟ್ ಇಲ್ಲಿ ನೋಡಿ ಇದು ಸ್ಟೀಪ್ ಆಗಿದೆ. ಇನ್ ಸ್ಪೈಟ್ ಆಫ್ ದಟ್ ಇಟ್ ವಿಲ್ ಗೋ ಟು ದ ಸೇಮ್ ಹೈಟ್, ಕಮ್ ಬ್ಯಾಕ್ ವಿತ್ ದ ಸೇಮ್ ಸ್ಪೀಡ್ ಅಂಡ್ ದೆನ್ ಗೋ ಬ್ಯಾಕ್. ಸೊ ದ ಸ್ಪೀಡ್ ವಿಲ್ ಬಿ ಸೇಮ್ ಇನ್ ಬೋತ್ ದ ಡೈರೆಕ್ಷನ್. ಈ ಡೈರೆಕ್ಷನ್ ಇಂದ ಬಂದಾಗಲೂ ಆ ಡೈರೆಕ್ಷನ್ ಇಂದ ಬಂದಾಗಲೂ ಅಟ್ ದ ಮಿಡಲ್ ಪಾಯಿಂಟ್ ಆರ್ ದ ಲೋಯೆಸ್ಟ್ ಪಾಯಿಂಟ್ ಅಲ್ಲಿ ಸೇಮ್ ಇರುತ್ತೆ. This is how he could connect the motion of the simple pendulum to the motion on the inclined plane. ಇದರಿಂದ ಒಂದು ವೆರಿ ಇಂಪಾರ್ಟೆಂಟ್ ಅಬ್ಸರ್ವೇಷನ್ ಬಂತು ಅವನಿಗೆ. ಇಲ್ಲಿ ನೋಡಿ, ಇದು ವೆರಿ ಫೇಮಸ್ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ನೋಡಿದ್ವಿ. ಇಲ್ಲಿ ಡಿಫ್ರೆಂಟ್ ಪ್ಲೇಸ್ ಅಲ್ಲಿ ನಾವು ನೇಲ್ ಹಾಕಿದ್ರೆ ವಿ ಸಿ ದಟ್ ದ ಸ್ಲೋಪ್ ಗೋಸ್ ಆನ್ ಚೇಂಜಿಂಗ್, ಬಟ್ ದ ಹೈಟ್ ಟು ವಿಚ್ ಇಟ್ ಗೋಸ್ ಅಪ್ ವಿಲ್ ಬಿ ದ ಸೇಮ್. ಇದೇ ಆರ್ಗ್ಯುಮೆಂಟ್ ಫಾಲೋ ಮಾಡಿ ವಿಲ್ ಸಿ ದಟ್ ಇಲ್ಲಿಂದ ರಿಲೀಸ್ ಮಾಡಿದ್ರೆ ಸೇಮ್ ಹೈಟ್ ಇದೆ, ಇಟ್ ಗೋಸ್ ಟು ದ ಸೇಮ್ ಹೈಟ್ irrespective of the slope of the inclined plane on the other side. So this led him to conclude about the conservation of mechanical energy. Very important conclusion. And this is the law of inertia which Sir Isaac Newton later adopted for stating his first law of inertia. This was Galileo's first discovery. ನೋಡಿ ನಾವು ಎಲ್ಲಿಂದ ಎಲ್ಲಿ ತನಕ ಬಂದ್ವಿ. ಒಂದು ಸಿಂಪಲ್ ಪೆಂಡುಲಮ್, ಒಂದು ಪೆಂಡುಲಮ್ ಮೋಷನ್, ಒಂದು ಶ್ಯಾಂಡಲಿಯರ್ ಮೋಷನ್ ನೋಡ್ಕೊಂಡು ನಾನು ಎಲ್ಲಿಂದ ಎಲ್ಲಿ ತನಕ ಇಟ್ಬಿಟ್ಟು. ಸೊ ಅಬ್ಸರ್ವೇಷನ್, careful measurement, meticulous measurement, attention to smallest structure, all led to the appreciation of hidden causes. ಏನೇನು ಮುಚ್ಕೊಂಡಿದ್ಯೋ ಅದನ್ನೆಲ್ಲ ಕಂಡು ಹಿಡ್ದ, ಅದನ್ನೆಲ್ಲ ಹೊರಗೆ ಬಂದ. ಬೂದಿ ಮುಚ್ಚಿದ ಕೆಂಡ ಅಂತ, ಬೂದಿ ತೆಗೆದ್ರೆ ಅದು ಕೆಂಡ ಏನೇನಿದೆ ಅದರ ಚೆನ್ನಾಗಿ ಗೊತ್ತಾಗೋಯ್ತು ನಮ್ಗೆ. ಸೊ ಜಸ್ಟ್ ಒಂದು ರೀಕ್ಯಾಪ್, ಇದನ್ನ ಇನ್ನು ಜಾಸ್ತಿ ಹೋಗಲ್ಲ, ಟೈಮು ಶಾರ್ಟ್ ಆಗಿದೆ. ದಿಸ್ ಇಸ್ ಫ್ರೀ ಫಾಲ್, ಪೆಂಡುಲಮ್ ಮೋಷನ್ ಅಂಡ್ ಇನ್ಕ್ಲೈನ್ ಮೋಷನ್. ಇಲ್ಲಿ motion on the inclined plane. If we compare here, the pendulum motion at this highest point is similar to that of the free fall. Illi as it comes down the arc, ಒಂದೊಂದ್ ಕಡೆನೂ ಒಂದೊಂದು ಟ್ಯಾಂಜೆಂಟ್ ನಾವು ಡ್ರಾ ಮಾಡಿದ್ರೆ ಇಲ್ಲೊಂದು ಆಂಗಲ್ ಸಿಗುತ್ತೆ. ಈ ಆಂಗಲ್ ಎಲ್ಲೆಲ್ಲಿ ಆ ಆಂಗಲ್ ಸೇಮ್ ಇದೆಯೋ, ನಾವು ಅಲಾಂಗ್ ದಿಸ್ ಪಾತ್ ಅಟ್ ದಟ್ ಇನ್ಸ್ಟೆಂಟ್ ಏನ್ ಆಂಗಲ್ ಮಾಡುತ್ತೋ ದ ಮೋಷನ್ ಇಸ್ ಸಿಮಿಲರ್ ಟು ದಟ್ ಆನ್ ಎನ್ ಇನ್ಕ್ಲೈನ್ಡ್ ಪ್ಲೇನ್. ಸೊ ಇವಾಗ ಮೋಷನ್ ಆಫ್ ಪೆಂಡುಲಮ್ ಅಂಡ್ ಮೋಷನ್ ಆಫ್ inclined plane ನೋಡೋದ್ನಲ್ಲ. So he assumed that the time taken for a bob to move along this arc is almost should be equal to the time taken for the ball to fall along this chord, or this he wanted to state a law of chords. Time taken to descend any chord in the quarter oscillation should be same as the time taken for it to go through this arc. So ಈ one quarter ನಾವು extend ಮಾಡಿದ್ರೆ we get a circle. He's assumed that the circular path is the isochronous path. ಇಲ್ಲಿ observe ಮಾಡಿ, simultaneously ಈ circumference ಇಂದ ನಾವು ಯಾವುದೇ ಪಾಯಿಂಟ್ ಇಂದನು at the same time ಡ್ರಾಪ್ ಮಾಡಿದ್ರೆ all of them would fall at the same time. He proved this experimentally, but ಅದನ್ನ ಮ್ಯಾಥಮೆಟಿಕಲಿ ಪ್ರೂವ್ ಮಾಡಕ್ಕೆ ಅವನಿಗೆ ಆಗ್ಲಿಲ್ಲ. ಸೊ ಬಟ್ ಈ ವರ್ಕ್ ನ ಅವ್ನ ಮೆಂಟರ್ ಅಂಡ್ ಫ್ರೆಂಡ್ ಒಬ್ರು ಇದ್ರು, ಅವ್ರ ಹತ್ರ ಶೇರ್ ಮಾಡ್ಕೊಂಡಿದ್ದಕ್ಕೆ he said, Galileo, you are a wonderful mathematician, but sorry to say, you are a very poor physicist. Just imagine, today he is the father of modern physics. Now, ಇವಾಗ ಇದೆಲ್ಲ ಆಗಿದೆ ಎಷ್ಟು ವರ್ಷ? ಇವಾಗ ನಾವು let us go fast. 1637 ಮುಂದೆ ಬಂದ್ಬಿಟ್ವಿ ನಾವು. ಇವಾಗ he's almost 73 years. 1584 ಅಲ್ಲಿ ಹುಟ್ಟಿದ್ದ, 73 years. He's almost blind, not completely blind. But then again he came back after so many years. He came back to his pet pendulum. ಯಾತಕ್ಕೆ? ಅವಾಗ ಒಂದು ದೊಡ್ಡ ಪ್ರಾಬ್ಲಮ್ ಇತ್ತು, ಗ್ರೇಟ್ ಲಾಂಗಿಟ್ಯೂಡ್ ಪ್ರಾಬ್ಲಮ್. ದೋಸ್ ಡೇಸ್ ಯುರೋಪ್ ಅಲ್ಲಿ ಮ್ಯಾರಿಟೈಮ್ ನೇಷನ್ಸ್ ಅಂದ್ರೆ, ಮ್ಯಾರಿಟೈಮ್ ನೇಷನ್ಸ್ ವರ್ ನೇಷನ್ಸ್ ವಿಚ್ ವಾಂಟೆಡ್ ಟು ಫೈಂಡ್ ನ್ಯೂ ಪ್ಲೇಸಸ್ ಆನ್ ಅರ್ತ್. ಆ ಪ್ಲೇಸ್ ವೆಲ್ತ್ ಎಲ್ಲ ತಗೋಬೇಕಿತ್ತು ಅವ್ರಿಗೆ, ಅಲ್ಲಿ ಜನಗಳನ್ನ ಸ್ಲೇವ್ ಮಾಡ್ಬೇಕಿತ್ತು. ದೇ ವಾಂಟೆಡ್ ಟು ಇನ್ಕ್ರೀಸ್ ದೇರ್ ಟ್ರೇಡ್, ದೇ ಎಕ್ಸ್ಪ್ಯಾಂಡ್ ದ ಕಿಂಗ್ಡಮ್, ದೇ ಗೆಟ್ ಪವರ್ ಅಂಡ್ ರಿಚಸ್ ಅಂಡ್ ಆಲ್ಸೋ ಎಕ್ಸ್ಪ್ಯಾಂಡ್ ದೇರ್ ರಿಲಿಜಿಯನ್. ಸೊ ಇದೆಲ್ಲ ಮಾಡೋದಕ್ಕೆ ದೇ ಸೆಂಡ್ ಶಿಪ್ಸ್ ಆನ್ ವಾಯೇಜಸ್. ಸೊ ಫಾರ್ ಸೆಂಡಿಂಗ್ ಶಿಪ್ಸ್ ಆನ್ ವಾಯೇಜಸ್ on sea, you should know your place, where you are, where is your position. So navigation on ships based mainly on the coordinates of latitude and longitude. Latitude andre enu, horizontal lines, north towards the north and south of the equator. Longitude and they move, these don't join. Horizontal lines, parallels of latitudes don't join. Other longitude, they go around the earth from east to west. They go from north to south, north south, the east to west. They meet at the north pole and south pole at the top and bottom. So longitude, this is one longitude. So this is longitude is either east or west to a reference line. Now we take Greenwich as the reference line. To find the latitude, they used the position of a sun or a pole star. A pole star ತಗೊಂಡು ಹೆಂಗೆ the angle the pole star made with the horizon would give them, because there is the table ittu. So for finding the latitude, basically you need to have a compass, you need to know the date, and the navigation table was prepared for finding the sun's position at noon, so you could easily find the latitude at the place. ಬೆಳಿಗ್ಗೆ ಹೊತ್ತು ಸನ್ ನೋಡಿ ಎಷ್ಟು ಮೇಲಿದೆ ನಿಮ್ಗೆ, the higher it is, the nearer you are from the equator. ರಾತ್ರಿ ಹೊತ್ತು pole star ನೋಡಿ, the higher it is, you are farther away from the equator. So it was very easy to find the latitude. ಆದ್ರೆ ಲಾಂಗಿಟ್ಯೂಡ್ ಹೆಂಗ್ ಕಂಡುಹಿಡಿಯೋದು? ನೀವು ಒಂದೇ ಲ್ಯಾಟಿಟ್ಯೂಡ್ ಅಲ್ಲಿ ಬೇರೆ ಬೇರೆ ಲಾಂಗಿಟ್ಯೂಡ್ ಹೋದ್ರೆ the position of the pole star doesn't vary. ಮತ್ತೆ ಹೆಂಗ್ ಹೋಗೋದು, ಹೆಂಗ್ ಕಂಡುಹಿಡಿಯೋದು? So there was one way. ಏನ್ ಮಾಡ್ಬೇಕಿತ್ತು ಅಂದ್ರೆ, if you could find the position of longitude, how to find? ಹೆಂಗಾದ್ರೂ ಮಾಡಿ pole star ಅಂತೂ ಮೂವ್ ಆಗ್ತಿಲ್ಲ, ಬೇರೆ ಏನಾದ್ರೂ there should be some value, something which changes as you move from east to west or west to east. What is that which changes? The time of the day. So ಈ time of the day ಹೆಂಗ್ ಮೂವ್ ಆಗತ್ತೆ, ಹೆಂಗ್ ಚೇಂಜ್ ಆಗತ್ತೆ, ನಮ್ಗೆ ಇದೆಲ್ಲ ಗೊತ್ತು. ಇಟ್ಸ್ ಜಸ್ಟ್ ರೀಕ್ಯಾಪಿಚುಲೇಷನ್. ಅರ್ತ್ 24 ಗಂಟೆ ಕಾಲದಲ್ಲಿ ಒಂದ್ಸಲ ರೊಟೇಟ್ ಮಾಡತ್ತೆ. ಸೊ ಅದಕ್ಕೆ ಫಾರ್ ಇನ್ ಎವ್ರಿ ಒನ್ ಅವರ್ ಅಲ್ಲಿ sun appears to move 15 degrees. So for every 15 degree of longitude, you move eastwards, the local time moves 1 hour forward. For every 15 degree you move westwards, the local time moves back 1 hour. So if the reference, now Greenwich tagotivalla, is the local time at that whichever place you are, and the time at this Greenwich is known, then the difference between the time will give you the longitude. So this was the problem they faced, and they needed an accurate clock. Unfortunately, ಅವತ್ತಿನ ದಿನ ಕ್ಲಾಕ್ಸ್ ಇದ್ದಿದ್ದು ಲ್ಯಾಂಡ್ ಅಲ್ಲಿ ತುಂಬಾ ಚೆನ್ನಾಗಿ ನಡೆಯೋದು, and mainly the clocks were used in monasteries. You can see here, monasteries ಅಲ್ಲಿ clock ಇದೆ, bell ಇದೆ, and they used to ring the bell so that the monks could know the time to meditate. But on seas, there was no clock which was able to withstand the temperature changes, weather changes, humidity changes, or the motion of the rocking of the ship at sea. So there were errors in navigation. Suddenly ಅವ್ರಿಗೆ ಗೊತ್ತಿಲ್ಲದೇನೆ ಲ್ಯಾಂಡ್ ಬಂದ್ಬಿಡೋದು, they would hit, shipwreck ಆಗೋದು. ಸಡನ್ಲಿ ಎಷ್ಟೋ ದಿನ ತನಕ ಲ್ಯಾಂಡೇ ಕಾಣಿಸ್ತಿರ್ಲಿಲ್ಲ, they used to get lost. So ರೇಷನ್ ಕಮ್ಮಿ ಆಗೋದು, ಮೆಡಿಸಿನ್ ಕಮ್ಮಿ ಆಗೋದು, so they used to die, people used to die on the way. ಇದೆಲ್ಲ ಪ್ರಾಬ್ಲಮ್. ಎರರ್ ಒಂಚೂರು ಆಗೋದ್ರೂ ಯಾತಕ್ ಆಗ್ತಾ ಇತ್ತು, ಯಾತಕ್ ದೇ ಟು ಲೂಸ್ ದೇರ್ ವೇ, ಏನಾಗ್ತಿತ್ತು ನೋಡೋಣ. ಇಲ್ಲಿ ಅರ್ತ್ ಸರ್ಕಂಫರೆನ್ಸ್ ನಮ್ಗೆ ಗೊತ್ತು ಎಷ್ಟಿದೆ ಅಂತ. ಸೊ ಒನ್ ರೊಟೇಷನ್ಗೆ 24 ಗಂಟೆ ಕಾಲ ತಗೊಂಡ್ರೆ ಎಷ್ಟು ಮಿನಿಟ್ಸ್ ತಗೊಳುತ್ತೆ? ಹಾಗೆ ಡಿಸ್ಟೆನ್ಸ್ ಟ್ರಾವೆಲ್, ಡಿಸ್ಟೆನ್ಸ್ ಕವರ್ಡ್ ಇನ್ 1 minute ಇಷ್ಟು 27 ಪಾಯಿಂಟ್ ಎಷ್ಟು. ಸೊ ಇವಾಗ 15 ನಿಮಿಷ ಎರರ್ ಆದ್ರೆ, ಒಂದಿನಕ್ಕೆ 15 ನಿಮಿಷ ಅವರು ಟೈಮ್ ಗೊತ್ತಾಗದೇ ಇದ್ರೆ, ಚೇಂಜ್ ಆಗದೆ ಇದ್ರೆ ಎಷ್ಟಾಗತ್ತೆ? ಡಿಸ್ಟೆನ್ಸ್ ವಿಚ್ ದೇ ವುಡ್ ಗೋ ಅವೇ ವಿಲ್ ಬಿ this much into 15, that is 416 kilometers. So ಅಷ್ಟು ದೂರ ಹೊಟ್ಟೋಗಿರೋರು ಅವರು, ಈ ಕಡೆ ಅಥವಾ ಆ ಕಡೆ. So they used to be away from the place where they wanted to reach. So ಈ 100 years, 1550 to 1650 ತನಕ 1 in every 5 ships were lost or had shipwreck or whatever it is. So ಇದರಿಂದ European maritime powers, they were frustrated and they wanted to somehow find the solution for the longitude. So they announced large amount of prizes for determining the longitude at sea. ಕೇಳಿಸ್ತಾ ಇದೆಯಾ? ಹಲೋ,
ಹೌದು ಮೇಡಮ್, ಹೌದು.
ಓಕೆ, longitude at sea. So ಇವಾಗ here is where Galileo comes in. Galileo competed for this longitude prize. He was in need of money at that time. He was almost blind also, but he had got an idea. First, he thought using the moons of Jupiter, using the astronomical events, he could find out the longitude. So he proposed his proposal to Holland, but then in 1637, he had an idea. He thought of a mechanism which would make the pendulum used in clocks for timekeeping. So, ಏನ್ ಕಂಡುಹಿಡ್ದ ಅವನು, ಏನ್ ಐಡಿಯಾ ಕಂಡುಹಿಡ್ದ ಅಂದ್ರೆ, he had an idea of an escapement mechanism. ಅಂದ್ರೆ ಇದು rotational ಎನರ್ಜಿನ lateral impulses ಆಗಿ ಕನ್ವರ್ಟ್ ಮಾಡುತ್ತೆ. This was the mechanism which he thought of. But since he was blind, he explained everything to his son, who drew a sketch of it. ಇದು ನೋಡಿ, just how it is moving. ಇದು ಕಾಣಿಸ್ತಿದೆ, ಇದು ಮೂವ್ ಆಗ್ತಾ ಇರೋದು. ಇಂಪಲ್ಸಸ್ ವರ್ ಗಿವನ್ ಇಲ್ಲಿ. ದಿಸ್ ಇಸ್ ಹೌ these were the various escapers. But both of them died before it was done or it was made. Galileo passed away. His
ಒಂದು ನಿಮಿಷ ಬಂದೆ. I think internet problem. Let's just come back. It's about to finish.
ಕಾಣಿಸ್ತಾ ಇದೆಯಾ? Okay.
Madam.
Okay. So now we have come to Christian Huygens. At a very young age, he showed very much interest in mechanics. At very young age of 17, independently he discovered the time square law, which Galileo had done. And 26 years idaga, he discovered the rings of Saturn. And ivaga, he was very much interested in astronomy. So the work in astronomy required accurate timekeeping. So he needed a device which would measure the time very accurately. It was then that he studied whatever Galileo had done. He found out that the isochronous path is not made by a circle. So mathematically he calculated and he proved that it is not a circle but a cycloid, which is the path of isochrony. This cycloid andre yenu? It is the path or it is the curve traced by a circle, a point on the circle when it slides without slipping on this. Nodi, this is the cycloid path. This is the circular path and this is the cycloid path. This cycloid path, if the pendulum is made to move, ಎಷ್ಟೇ ಆಂಪ್ಲಿಟ್ಯೂಡ್ ಇಂದ ಎಷ್ಟೇ ಹೈಟ್ ಇಂದ ನೀವು ಹಾಕಿದ್ರು all the bodies, they are coming here at the same time, or the time period will be the same. In case what Galileo ಮಾಡಿದ ಕಡೆ amplitude ಜಾಸ್ತಿ ಆದಾಗ time period had slowed down ಆಗಿರಲಿಲ್ಲ. He could not prove it because circle is not the path of isochrony. ಇದು circular path, ಇದು cycloidal path. So I think you could understand the difference between circle and cycloid. So now he understood the cycloid is the path, but the pendulum goes in a circular path. So ಏನಾಗತ್ತೆ? ಹೆಂಗ್ ಮಾಡೋದು cycloid path ನ? So he used the two chops, cycloidal chops. ಈ two curved pieces na ee ಜಾಗದಲ್ಲಿ ಇಟ್ಟು he forced the pendulum to move along the cycloid. See? And along with this, you can see the chops or the cheeks as you call. So they were forced to move. So ee ಜಾಗದಲ್ಲಿ ಎಷ್ಟೇ ಜಾಸ್ತಿ amplitude ಆದ್ರೂ ಕೂಡ it will have the constant time period. So ಇದೊಂದಲ್ದೇನೆ ಇನ್ನೊಂದು ಏನ್ ಮಾಡ್ದ ಅಂದ್ರೆ ಅವನು he used metal rods instead of the principle of compound pendulum ಅನ್ನೋದನ್ನ ಯೂಸ್ ಮಾಡಿ ರಾಡ್ ಯೂಸ್ ಮಾಡಿ he with silk thread ಯೂಸ್ ಮಾಡ್ತಿದ್ರಲ್ಲ ಪೆಂಡುಲಮ್ಗೆ ಅದನ್ನ ತೆಗೆದ್ಬಿಟ್ಟು he used a principle of compound pendulum to this, and he made the first clock. He was the first person who made the pendulum clock. He patented it also, and then he wanted to have it. He was sure that in spite of the amplitude, large amplitude, small amplitude, different weather conditions, this pendulum could withstand the sea trials. And then he made a seconds pendulum. Seconds pendulum anodu, the pendulum whose time period is exactly 1 second. Adanna he wanted to send it for sea trials. So ಎರಡು ಸಲ ಆಯ್ತು. In 1663 and 64, when Robert Holmes went from London to Lisbon, and in second time he went from Guinea to Atlantic, and he returned. His journey proved fruitful, and Highgates was very happy that this clock could be used as a navigational aid. But 1672 ನಲ್ಲಿ Jean Richard ಅವನು ಒಬ್ಬ ಸೈಂಟಿಸ್ಟ್ ಆಗಿದ್ದ. he went on an expedition from Paris to Cairns. ಎಲ್ಲಿದೆ ಪ್ಯಾರಿಸು, ಎಲ್ಲಿದು ನೋಡಿ, ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಬಂದು he went back. His main aim was to test the length of the seconds pendulum. So ಇಲ್ಲಿ seconds pendulum ನೋಡ್ಬಿಟ್ಟು ಅಲ್ಲಿಂದ when he traveled to this place, he found that the period became slow. It started beating slowly. It went slow when it reached this point. He reported this. So what Huygens concluded was maybe the humidity was there which slowed down, or heat lengthened the pendulum, or friction increased at tropics, and so on. So ಏನ್ ಆಗಿತ್ತು actually ಇಲ್ಲಿಂದ ಇಲ್ಲಿ ಹೋದಾಗ, let us see now. ಇವಾಗ along with the longitudes and latitudes I am giving you, ಈ longitude ನೋಡಿ, there is a difference. So as he neared the equator, the time period has slowed down. So there was some factor which he could not understand. Now he has solved the longitude problem, but why it was beating slowly. So now to avoid this, maybe the pendulum problem agide anta anbiಟ್ಟು ಅವನು spring isochronous path follow ಮಾಡುತ್ತೆ ಅಂತ he used springs in his clocks, and then again it was sent on a trial in 1686. 1686 ಅಲ್ಲಿ ಏನಾಯ್ತು, ಇಲ್ಲಿಂದ ಹೋದ್ರು ಕೇಪ್, ಇಲ್ಲಿಂದ ಹೋಗಿ they have gone to this place, but on the way the person died. So anyhow a report ತಗೊಂಡ್ಬಿಟ್ಟು ನೋಡಿದಾಗ they also found out the same result. So ಏನ್ ಆಗಿರ್ಬೋದು ಇದಕ್ಕೆ ಅಂತ ಅರ್ಥ ಆಗ್ತದೆ. What is actually happening when you are moving from Paris to Cairns? They were not able to understand. So now Huygens again argued that this is because of variation of gravity. Gravity changes as you go near the equator, because Cairns is nearer to the equator than Paris. So ಇಲ್ಲಿ equator ಇಲ್ಲಿ G ವೇರಿ ಆದ್ರೆ ಡೆಫಿನೆಟ್ಲಿ T ನು ವೇರಿ ಆಗುತ್ತೆ. If G increases in equator, definitely T has to be decreasing, or vice versa. So ಇದರಿಂದ ನಮ್ಗೆ ಇನ್ನೊಂದು ಇಂಪಾರ್ಟೆಂಟ್ ಪಾಯಿಂಟ್ ಬಂತು. ಅರ್ತ್ ಇಸ್ ನಾಟ್ ಸ್ಫೆರಿಕಲ್, ಬಟ್ ಇಟ್ ಇಸ್ ಫ್ಲಾಟನ್ ಎಟ್ ದ ಪೋಲ್ಸ್. Cairns nearer the equator ಇದೆ, it is farther from earth core or earth center than Paris. So ಅಷ್ಟು ದೂರ ಇರೋದ್ರಿಂದ, ಸೊ ಇದನ್ನ ಐಸಕ್ ನ್ಯೂಟನ್ and Christian Huygens ಇಬ್ರು ಸೇರಿ they found out this. And another important point was because G varies, ಅಲ್ಲಿ ತನಕ G ಸೇಮ್ ಇರುತ್ತೆ, acceleration due to gravity G ಸೇಮ್ ಇರುತ್ತೆ ಅನ್ಕೊಂಡಿದ್ರು, but they have seen it is varying. So now we have got the distinction between the mass and weight. ನೋಡಿ ಹೆಂಗೆ ಈ ಪೆಂಡುಲಮ್ ತನ್ನ ಸಿಂಪಲ್ ಹಂಬಲ್ ಪೆಂಡುಲಮ್ ಟ್ರಾವೆಲ್ ಮಾಡ್ತಾ ಓವರ್ ದ ಇಯರ್ಸ್ ಏನೇನ್ ಡಿಸ್ಕವರಿಗೆ ಇಟ್ ಇಸ್ ಗಿವಿಂಗ್ ರೈಸ್ ಟು. ಸೊ ಇಷ್ಟೆಲ್ಲ ಆಯ್ತು. ಸೊ ದಿಸ್ ಮಚ್ ದೇ ಫೌಂಡ್ ಔಟ್. ಸ್ಟಿಲ್ ದ ಕ್ಲಾಕ್ ವಾಸ್ ನಾಟ್ ವೆರಿ ಮಚ್ ಗುಡ್ ಆನ್ ಸಿ. ಸೊ ಇನ್ 1707 ದ ವರ್ಸ್ಟ್ ಡಿಸಾಸ್ಟರ್ on sea took place. British commander took a fleet, 5 ships were traveled from Gibraltar to England. When they were here, they miscalculated their longitude. So they turned a little too late. Actually, they were here, but they thought they were at this point. This was the actual route, but they miscalculated. The planned route was like this. They had to go to the English Channel. Ilinda bandu allige hogbekittu. But ಇಲ್ಲಿ ಹೋಗಿ they turn ಮಾಡಿದಾಗ they hit the island, Scilly Islands hit ಆಗಿ shipwreck ಆಗಿ more than 2,000 lives were lost. Big tragedy. So ಏನಾಯ್ತು ಇಲ್ಲಿ actually miscalculation of longitude ಆಯ್ತು. What it caused, ಏನ್ result ಆಯ್ತು? Shipwrecks and deaths ಆಯ್ತು. What were the lessons learned? So there was a huge demand for safer navigation. So ಇದರಿಂದ there was a famous Longitude Act of 1714. There was a huge amount, 20,000 pounds were to be given to the first person who could discover the means of finding the determined longitude at sea. In comes John Harrison. He was not a formal, he did not have formal education. He was a self-educated, he was a clockmaker. He was not a big scientist as his predecessors, but he was fond of watches. He was fascinated of watches from the age of 6. When this announcement of the prize was made, he was only 21. Remember, he was only 21. Now, he studied, hello, he studied the problems. He came to the conclusion that the temperature, humidity, and motion of the ships were the things which were giving the problem of timekeeping at sea. So time of this pendulum clock dependent on G. If G dependency ne change ಮಾಡಿಬಿಟ್ರೆ ಏನಾಗುತ್ತೆ? And ಇನ್ನೊಂದು ಏನಾದರೂ hello.
Please go ahead, ma'am.
Okay. So he showed that metallurgy, not mechanics. Mechanics ಒಂದೇ ಅಲ್ಲ, metallurgy can solve this problem. So bimetallic strip ಅಂತ ನಾವಿವಾಗ ಕೇಳಿದೀವಲ್ಲ, he used alternate ferrous, iron and zinc rods so that if one expanded, the other one compensated. They had different thermal expansions. So to compensate for the temperature problem, he designed a gridiron pendulum anta. And then next to motion of this ship, waves up and down hogutte, so idagate, back and forth agate. And then heng madodu, ivaga pendulum adre amplitude ಜಾಸ್ತಿ ಕಮ್ಮಿ ಆಗುತ್ತೆ. What he did, he used springs, counterweights at the top of the clock, so that they would swing back and forth to act as shock absorbers. So rock and roll of the ship na avoid ಮಾಡೋದಕ್ಕೆ. Now finally he could make a clock which was seaworthy at last. 21 years ಇದ್ದಾಗ 1714 ಅಲ್ಲಿ ಅನೌನ್ಸ್ ಆಗಿದ್ದು. He started building his clock. First 5 years ತಗೊಂಡ to make the first very famous H1 clock ಅಂತ ಕರೀತಾರೆ ಅದಕ್ಕೆ. It was oil free. Oil ಮತ್ತೆ ಚಳಿಗಾಲದಲ್ಲಿ ಗಟ್ಟಿ ಆಗೋದು, ಇದಾಗಿ lubrication problem ಆಗೋದು. So ಈ ಕ್ಲಾಕ್ಗೆ ಆಯಿಲೇ ಬೇಕಿಲ್ಲ. It was pendulum free. It was resistant to change in temperature and humidity, and it was taken for a test run. So Ali performed very well. So now here was a clock which was trustworthy and seaworthy. Then he wanted to improve on this. He made a few more watches, H2, H3. In H2 he discovered some flaw. In 2 ವರ್ಷದಲ್ಲಿ ಮಾಡ್ದ some flaw ಇತ್ತು. So again he wanted circular balances. Rod balances ಬದಲು circular bar balance ಬದಲು circular balance ತಗೊಂಡು he made H3, which he took 17 years to make. And ಇದಿಷ್ಟು ಮಾಡೋದ್ರೊಳಗೆ ಏನ್ main ಇದು bimetallic strip and cage roller bearing. These were the two important things which he gave to the world. Finally, in 1761, he made the first sea watch. ಮೊದಲನೇದು almost 1 meter ಇತ್ತು, 6 to 7 centimeter ಗಿಂತ ಜಾಸ್ತಿ ಇತ್ತು. ಇದು only 13 centimeter in diameter. He was very happy with this. Later on, he made another H5. ಅದು ಯಾತಕ್ಕೆ ಅಂತ ಆಮೇಲೆ ಹೇಳ್ತೀನಿ. So these 3 clocks, see, compare. ಇದು 13 centimeter ಇದೆ, ಇದು almost 1 meter ಇದೆ. These were the 5 clocks which he made. The first trial to Jamaica, it proved very accurate. And he went to claim his prize, but you know how the parliament was even in those days. They refused to give him the prize. They said maybe it was a fluke. ಇನ್ನೊಂದ್ಸಲ ಟೆಸ್ಟ್ ಮಾಡಬೇಕು, ಇನ್ನೂ ಜಾಸ್ತಿ ಟೆಸ್ಟ್ ಮಾಡಬೇಕು ಅಂತೆಲ್ಲ ಹೇಳಿದ್ರು. So one of the board members, he himself was wanting the prize. So based on the moon, position of the moon, he wanted to calculate the longitude. So ಇದನ್ನ ಕಾನ್ಫಿಸ್ಕೇಟ್ ಮಾಡ್ಬಿಟ್ಟು ನಾನು ಇಟ್ಕೊಂಡ್ಬಿಟ್ಟ, ಅವ್ನು ಕೊಡ್ಲೇ ಇಲ್ಲ, ಅವ್ನು ವಾಪಸ್ ಆ ಗಡಿಯಾರನ ನಾನು ಟೆಸ್ಟ್ ಮಾಡ್ತೀನಿ ಅಂತ ಅಂದ್ಬಿಟ್ಟು ಅವನ ಹತ್ರ ಇಟ್ಕೊಂಡ್ಬಿಟ್ಟ. So in frustration, he made another clock, another watch, H5, and then he made an appeal to King George III. And he had to intervene to get Harrison his full reward. Even then, he didn't get the full, he got only part of it. But over the years, 20,000 ಗಿಂತ ಜಾಸ್ತಿನೇ ಸಿಕ್ತು. ಯಾಕಂದ್ರೆ every time he used to get only part of it to work upon the problem of this. So by that time, he was already 80 years old. So 21 to 73, 40 years, he went on working for the clock. And he died, and another 3 years later, he died. He died on the same date he was born. So he spent his entire lifetime solving a very tough problem, but he was successful in the end. And this benefited the whole world, and also, and mainly, the field of maritime navigation. So this was the whole journey of the clock. And the pendulum clock in 1930s tankanu, it was perfect. 15 minutes in a year or 15 seconds in a year or change agodu. But then in 1930s we have got quartz clock, and now ivatin dina niಮಗೆ ಗೊತ್ತು atomic clock ide, so and so on. But still in many houses we have got this grandfather clock, the pendulum moving to and fro. ನೋಡಕ್ ಬಹಳ ಚೆನ್ನಾಗಿರುತ್ತೆ. So you see, from ಸಿಂಪಲ್ ಪೆಂಡುಲಮ್ 16th ಸೆಂಚುರಿ ಅವನು ಯಾವಾಗ ನೋಡ್ದ, 1583 ನಲ್ಲಿ ಅಬ್ಸರ್ವ್ ಮಾಡ್ದ, ಆಮೇಲೆ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಮಾಡಿದ್ದು 1600 ಅಲ್ಲಿ. ಸೊ ದೀಸ್ ಆರ್ ಆಲ್ ದ ಥಿಂಗ್ಸ್ ವಿಚ್ ವಿ ವೆಂಟ್ ಥ್ರೂ. ವಾಟ್ ಎ ಮ್ಯಾಗ್ನಿಫಿಷೆಂಟ್ ಜರ್ನಿ ಫಾರ್ ಎ ಸಿಂಪಲ್ ಹಂಬಲ್ ಪೆಂಡುಲಮ್. I think I have come to the end. I don't know what is the time. Another 4 minutes, I think, for the 5.
Yes, madam. Yes, madam. Yes, madam.
So we come to the end of not my journey, Simple Pendulum's journey. So, any students having anything to say?
Madam, really, it was an excellent presentation. I myself didn't know that Simple Pendulum's application is so much, and so many laws are there behind Simple Pendulum. The great presentation, madam.
Thank you so much.
In a very simple language, you have explained. I'm sure students will be highly benefited by your talk, madam.
I just thank you so much. ಇದನ್ನ ಚೂಸ್ ಮಾಡಿದ ಯಾಕೆಂದ್ರೆ 11th ಅಲ್ಲಿ ಇದೆ ಈ ಕೋರ್ಸು, ಸಿಂಪಲ್ ಪೆಂಡುಲಮ್ದು ಇದು ಎಲ್ಲ. ಬಟ್ ನಾವು ಸುಮ್ಮನೆ ಅದು ಸ್ಟಡಿ ಮಾಡ್ಬಿಡ್ತೀವಿ. ಹಿಂದೆ ಎಷ್ಟು ಜನದ್ದು ಹಾರ್ಡ್ ವರ್ಕ್ ಇದೆ, ಎಷ್ಟು ಜನದ್ದು ಕಾಂಟ್ರಿಬ್ಯೂಷನ್ ಇದೆ, ಓವರ್ ಸೋ ಮೆನಿ. ಯಾವಾಗಿಂದ ಶುರುವಾಗಿ ಎಲ್ಲಿ ತನಕ ಹೋಯ್ತು. ಸೊ ಐ ವಾಸ್ ಇಂಟ್ರೆಸ್ಟೆಡ್ ಇನ್ ದಿಸ್ ಟಾಪಿಕ್, ಸೊ ಐ ಜಸ್ಟ್ ಥಾಟ್.
ತುಂಬಾ ಚೆನ್ನಾಗಿತ್ತು ಮೇಡಮ್. ನಮ್ಮ ಫಿಸಿಸಿಸ್ಟ್ ನಮ್ಮ ಪ್ರೊಫೆಸರ್ ಮೂಲಿಮನಿ ಸರ್ ಇದ್ದಾರೆ. ಲೆಟ್ ಅಸ್ take his
madam, it was a very, very beautiful, and it was really an adventure. You just can't imagine, though I've studied physics, but so many details were not known to me. Particularly students get confused, with regard to the relation between a simple pendulum, motion on an inclined plane, all that connectivity, free fall. Beautifully it has come out. That is what is needed. Whole lecture shows to the students how science is done. That is, how much effort goes into science. That is what we have to teach the students. Discovery of science in schools means what you have told today. It's really wonderful. I am not going to praise it, but many, many things. Fantastic journey. It's I am sure the journey will continue, but it's
thank you so much.
Thank you. I'm grateful personally for knowing many things. Thank you.
Thank you so much. Actually, I wanted to go through the escapements also. Escapement allu tumba advantage, revolution aitu. Galileo escapement in the anchor escapement aitu, grasshopper escapement aitu. But anyhow, adella avರಿಗೆ beyond their ಇದು ಆಗುತ್ತೆ.
ರಿಕ್ವೆಸ್ಟ್ ಅಂದ್ರೆ ಇದು ಒಂದು ನೀವು ಬುಕ್ ಫಾರ್ಮ್ ಬುಕ್ಲೆಟ್ ಅಲ್ಲಿ ತಂದಿದ್ರೆ ಬಹಳ ಯೂಸ್ಫುಲ್ ಆಗುತ್ತೆ. ಪರ್ಟಿಕ್ಯುಲರ್ಲಿ ಕ್ಲಾರಿಫೈಯಿಂಗ್ ದ ಕಾನ್ಸೆಪ್ಟ್ಸ್ ಆಫ್ ಫ್ರೀ ಫಾಲ್, ಇನ್ಕ್ಲೈನ್ಡ್ ಪ್ಲೇನ್, ಸೋ ಮೆನಿ ಥಿಂಗ್ಸ್ ಬಹಳ ಕ್ಲಿಯರ್ ಇಲ್ಲ ಹುಡುಗರಿಗೆ.
Yes, sir.
I hope I was able to. I was of a little help ಅವರುಗಳಿಗೆ.
Thank you.
ಚೆನ್ನಾಗಿತ್ತು ಮೇಡಮ್. ನೆಕ್ಸ್ಟ್ ತಮಗೆ ಇನ್ ಯಾವ್ದಾದ್ರು ಇಂಟ್ರೆಸ್ಟಿಂಗ್ ಸಬ್ಜೆಕ್ಟ್ ಅನ್ಸಿದ್ರೆ ಟಾಪಿಕ್, KSTA will be very happy to host once again, madam. From
Okay,
June
okay.
onwards, we'll again start online classes for PU students, mostly first
Okay.
year PU. Our Matinasari invite ಮಾಡ್ತೀವಿ, madam. We are
Okay.
very grateful to you for your time and excellent presentation. Thank you.
I really thank you all for this wonderful opportunity you have given. Frankly to speak, this is my first online presentation. ನಾನು ಯಾವಾಗಲೂ ವರ್ಕ್ಶಾಪ್ಸ್ ತಗೊಂಡಾಗ ಫಿಸಿಕಲಿ ತಗೊಳ್ತೀನಿ. ದಟ್ ವಾಸ್ ಮೋರ್ ಈಸಿ ಫಾರ್ ಮೀ. ಐ ವಾಸ್ ಅಪ್ರಿಹೆನ್ಸಿವ್ ಇದ್ರೊಳಗೆ ಆನ್ಲೈನ್ ಹೆಂಗಾಗತ್ತೋ ಏನೋ ಅಂತ.
ಇಲ್ಲ, ತುಂಬಾ ಚೆನ್ನಾಗಿತ್ತು, ತುಂಬಾ ಎಕ್ಸಲೆಂಟ್.
ಥ್ಯಾಂಕ್ ಯು ಸೋ ಮಚ್.
I'm also very thankful to Professor Mulimani sir. ಬೆಳಿಗ್ಗೆಯಿಂದ ನಮ್ಮ ಜೊತೆನೇ ಇದ್ದಾರೆ. In between.
Thank you very much, Professor Mulimani sir. I am really thankful to you for giving your valuable time. ಇಷ್ಟು busy schedule.
I am benefited immensely. It's not to just say. Thank you.
ಬೆಳಿಗ್ಗೆ we had one more online program. Sir was there, and
Okay.
in the evening, sir again joined. Sir, on behalf of KSTA, very thankful to you. Your presence always inspires us to organize many such programs in the coming days. Grateful to you, sir. I'm also thankful to all the participants and my colleagues for organizing this webinar. Thanks, madam. Thank you very much.
Thank you very much. Namaskar. Namaskar. Namaskar.
Madam, if possible,
Okay.
if you can give a few pages of notes,
Yeah.
then bring it out in the
Yes.
in our book. I mean,
Points ಆಗಿ ಮಾಡಿದ್ದೀನಿ. I'll try to write it in a expanded form. ಬರೀ ಪಾಯಿಂಟ್ಸ್ ಬರ್ಕೊಂಡಿದ್ದೆ.
ಹೌದು.
I'll do it. Thank you so much.
Yes.
Thank you so much. ನಮಸ್ಕಾರ.
ನಮಗೆ ಡಿಗ್ರಿ ಸಿಂಪಲ್ ಪೆಂಡಲಮ್ ಬರ್ತಾರೆ. ಬಾರ್ ಪೆಂಡಲಮ್